January 28, 1986. Millions of us were glued to our TVs, watching the Space Shuttle Challenger climb into this brilliant blue Florida sky. It was a symbol of everything we could achieve. And then, just 73 seconds later, that symbol was gone, shattered into a plume of white smoke. So today, we're going to dig into how one of the most complex machines ever built was brought down by a failure that was, believe it or not, shockingly simple.
And that's really the question at the heart of this whole tragedy, isn't it? How could a $1.9 billion spacecraft, the pinnacle of technology, carrying 7 people's lives, fail because of a simple rubber ring? Well, the answer is an incredible story of science, of pressure, and of a critical warning that was tragically ignored. But before we get into the nuts and bolts of the failure, you have to understand the promise of this mission. This wasn't just another trip to orbit. The whole idea behind the space shuttle was to make spaceflight seem, well, routine, almost normal. And for this flight, its 25th mission, NASA was about to take that idea to a whole new level.
Yeah, they were sending a teacher, Krista McAuliffe. She was a 37-year-old from New Hampshire, and she was chosen from over 11,000 other teachers to be the very first private citizen in space. Her job? To broadcast lessons from orbit right into classrooms across the country. She wasn't a test pilot, she wasn't some PhD physicist, she was one of us, and she was carrying the dreams of an entire nation with her.
But underneath all of that excitement and all of that hope, a critical design flaw was basically hiding in plain sight. And to understand what went so horribly wrong, we need to zoom in from that big national dream to the hard science of failure, right inside the shuttle's most powerful engines. So getting the Challenger off the ground required these 2 massive solid rocket boosters, or SRBs. And let me tell you, these things were and still are the most powerful solid fuel rockets ever flown. They were so enormous they had to be built in separate pieces, shipped by train, and then stacked together on the launch pad like some kind of colossal set of building blocks. And here it is. This is the crucial point. Each joint between those massive segments was sealed by 2 giant rubber gaskets. We call them O-rings. Their job sounds simple, but it was absolutely vital. They had to contain the 5,800-degree Fahrenheit gas that was roaring inside that booster. We're talking hotter than molten lava. If that gas ever got out, well, the consequences would be catastrophic. This really gets to the heart of the problem. See, rubber has a weakness. It does not like the cold. A nice, warm O-ring is flexible, it's springy. When that rocket ignites, the pressure instantly squishes it into the joint, making a perfect seal in just milliseconds. But a cold O-ring gets stiff, it gets hard, it loses that springiness, which means it seals way too slowly, or maybe not at all. And here's the thing, this wasn't some hidden secret. This weakness was a known risk. And that brings us to the human part of this disaster, because engineers were desperately trying to sound the alarm on the very eve of the launch. Just picture it. The night before launch off, in sunny Florida, the temperature at the Kennedy Space Center just plummeted. It dropped to a record-breaking 18 degrees Fahrenheit. That's -8 Celsius. There was literally ice hanging off the launch tower. For the engineers at Morton Thiokol, the company that built the boosters, this one number was an absolute nightmare scenario. That evening, the Thiokol engineers, completely terrified by this cold front, scrambled to get NASA management on an emergency conference call. They'd seen problems with O-rings before in other missions, but nothing had ever gone wrong, so this dangerous sense of complacency had started to creep in. For hours, the engineers argued. They pleaded, saying this extreme cold pushed the risk way beyond anything acceptable. But under huge pressure to keep the launch schedule moving, NASA managers overruled them. They gave the final go for launch. The seriousness of that moment was captured perfectly by one of the engineers, a man named Roger Borjoli. His warning was just chillingly clear. He told them, "We are only qualified to 53 degrees, and launching in the cold," he warned, "could lead to a catastrophe of the highest order." His words would become a haunting prophecy. And so, against the direct, explicit warnings of the people who designed the system, Challenger was cleared to fly. So now let's break down those final 73 seconds, because every tick of the clock reveals another step in this unfolding disaster. Less than a second after ignition, at just 0.678 seconds, launch cameras caught the very first tiny sign of trouble. It was a small puff of dark gray smoke coming from a joint on that right-hand booster. You'd blink and you'd miss it. That was the cold, stiff O-ring, already failing to do its job. But then, something almost miraculous happened. The leak wasn't immediately fatal. By just a bizarre twist of fate, some byproducts from the burning rocket fuel created a temporary plug of slag that actually resealed the damaged joint. For a few precious seconds, the shuttle kept flying, with a ticking time bomb on its side that nobody knew about. Then, at 37 seconds into the flight, disaster found its next ingredient. The shuttle flew directly into the worst wind shear ever recorded during a launch. The whole vehicle was shaken violently, and these enormous forces put incredible stress on that compromised joint with its makeshift plug. At 59 seconds, that plug gave way. A searing flame, now totally visible against the dark sky, started jetting out from that exact same joint. The seal had failed completely, and this time, it was for good. That escaping jet of superheated gas acted like a precision blowtorch. In just a few seconds, it sliced right through the metal strut holding the booster to the big external fuel tank. Now, with its bottom support gone, the booster swiveled, slamming right into that central tank, which was packed full of explosive liquid hydrogen and oxygen. At 73 seconds after liftoff, the external tank ruptured. The super-cold fuels mixed and instantly ignited, creating a massive silent fireball in the thin air that completely swallowed the orbiter. Now, this is a really important point. The shuttle didn't explode in the way we think of a bomb. It was traveling at over twice the speed of sound when its structure failed, and it was torn apart by these just incredible aerodynamic forces. The crew cabin actually broke away mostly intact and continued upward before falling for miles into the ocean below. In the aftermath, a stunned world demanded answers. A presidential commission was put together to figure out the truth, and one of its members would cut through all the bureaucracy and technical jargon with a single moment of pure, brilliant scientific clarity. And that member was Richard Feynman. He was a Nobel Prize-winning physicist and a famously curious, no-nonsense kind of guy. He was getting really frustrated with the bureaucratic answers from NASA officials, so he decided he was going to do his own little investigation. And what he did next was just pure genius in its simplicity. During a televised hearing, right there at the witness table, he took a small C-clamp and a piece of the O-ring material. He squeezed it flat on the clamp, and then he dunked it into a glass of regular old ice water for a few moments. After he pulled it out of the water, he released the clamp, and the rubber just stayed compressed. It didn't spring back. He held it up for the cameras, for the whole world to see, and delivered the simple, devastating conclusion that explained everything. The cold rubber had lost its resiliency. In that one simple moment, he showed everyone the cold, hard truth. The Challenger disaster was a brutal, heartbreaking lesson, paid for with the lives of 7 brave explorers. It taught us that when you're reaching for the stars, there is no such thing as a small detail. And it taught us that the pressure to keep moving forward must never, ever overrule the hard evidence of science. It's a lesson that changed spaceflight forever.